We are very happy today to have Aram Harrow from MIT, where he's a professor. Aram has been a pioneer in quantum computing and quantum information, working, I guess, for 20 years now. Right? But Aram's papers, I've been reading them for a long time, and they really come in, well, at least two different varieties. One variety of Aram Harrow paper is that there's a field that has become very technically developed and sophisticated. The techniques are hard. All the papers are long and complicated. And then there's a paper by Aram, which is 2 or 3 pages long, which discovers a new and simple and beautiful idea that had been under everybody else's noses and they missed it. And that's happened multiple times in the really beautiful papers. And the other kind is where he engages with some topic that is thorny and technical and hard, and he uses really masterful insights to make real progress. And so I don't know what we're going to see today, but I'm looking forward to it. Aaron, take it away.
Thanks, Patrick, for the invitation and a very nice introduction. There's a third kind of paper, probably the most common one, which is one that hasn't appeared yet, which is what you'll see today. But I hope we'll get it out of the archive before too long. And it's it is about an old topic, which is how can we use quantum walks for algorithmic speedup. And I'll tell you about an algorithmic speedup that was very intriguing to me because of how isolated it was. It was like the platypus of quantum algorithms. And this represents our attempt to maybe find the larger, what's above species, phylum or something, group of animals that this thing belongs to. It's with my grad student Shankar Balashubramanian, who is going to spend some time at KITT, so that's almost local, and Tong-Ying Li, a former postdoc who is now at Peking University. So I'm going to talk about quantum walks, and to motivate them, I mean, this is kind of motivating from a computer science point of view. I think if you're a physicist, maybe quantum walks are already pretty natural, but I think nice in any case to think about the analogy between quantum and classical walks. So I'll begin with classical walks, which are defined in terms of a graph. Is it easy to show like just the front lights, or that they can be like in mobile speed? I'm not sure actually. Well, just that's even better, right? So you can see here faintly the little graph connecting these. This is an example of a graph hypercube. And mathematically, we can express it by its adjacency matrix, which just puts a 1 where there's an edge and a 0 if not. We'll only do undirected graphs today. A related matrix, which is useful for thinking about walks, is the graph Laplacian. It's like a graph version of the calculus Laplacian, but for some reason with the opposite sign. It's just you put the degrees along the diagonal, and then you subtract the adjacency matrix. And if the graph is regular, then that's just adding the multiple of the identity, the degree times identity, minus the adjacency matrix. And this relates to the random walk as follows. We can think of a random walk. It can be discrete or continuous time. Continuous time is kind of more convenient. The way that works is you have a probability distribution P over all the vertices, and that's evolving in time. And what does it mean to be a continuous time random walk? It means, according to a Poisson clock, you make a jump from your vertex to a random neighbor. And then that probability distribution is going to evolve, and probability is going to flow out of each vertex at a rate proportional to its degree, and it'll flow into each vertex from all the neighbors. And so you just naturally get dT is minus the Laplacian times the linear differential equation. The matrix is given by the Laplacian. So that's one place where it's very natural, describes the dynamics. You can also think of it as an observable or quadratic form. So if I have a vector b defined over all of the vertices, so b has an entry for each vertex, I can talk about b transpose LB, like the expectation value of L relative to the state b, and that just gives me the sum over all the edges of the squared difference between b on those edges. So what that means is that all the eigenvalues of L are not negative. The 0 eigenvector corresponds to just the constant function, at least if it's connected graph, or at least something that's a function that's a vector that's constant on each connected component. And then the higher the more the variation, higher variation corresponds to higher values of this quadratic. And we'll see that as an intuitive way to think about the eigenvalues and eigenvectors of L. is that higher eigenvalues correspond to more variation across those. Okay, so this is how to think about classical random walks. Oh, and one thing I'll further say is, related to this differential equation, the zero eigenvector is the thing that doesn't change at all. That's the constant vector, and that's basically the normalization part of a probability distribution. Probability distribution always adds up to 1, and that will not change when you do a random walk, right? That stays the same. And everything else decays. And the slow variations decay rapidly, and the rapid variations, the slow variations decay slowly, and the rapid oscillations decay quickly. And so that, if you think about this in spectral terms, that's what you get. Okay, so what's the quantum version? Well, first let me tell you about continuous space as well as continuous time. Then you get the diffusion equation. Now the probability distribution is a function of position and time. Again, you have a differential equation in terms of the Laplacian. Now it's just the calculus Laplacian. And from this, the Schrodinger equation is almost the same thing, except we put in a factor of, now we're doing amplitude, and now we put in an I. So, whereas in the diffusion equation, things are decaying, in the Schrodinger equation, things are oscillating. Okay, that's the main difference. And this has a number of profound consequences. Turns out, of course, the Schrodinger equation is a lot richer than the diffusion equation. The diffusion equation can't have something with momentum, for example. Everything just spreads out, but the Schrodinger equation, gives us everything we see in the world. From an algorithm point of view, what does it mean? Well, classical random walks are a good way of randomly sampling from some large space because of this mixing property. Like I described for the hypercube, but it could be any combinatorially defined space. If you make little local moves, like over the set of graph coloring or something, generically you'll randomly explore the space because it mixes. Quantum walks don't mix. Everything, no information is lost, everything is unitary. Instead, they give you a reflection. So to illustrate that, let's just look at the line. So this is your graph. I don't know if I put these double-sided. It's just, the graph is just the 1D line. So what are the eigenvalues and eigenvectors of the Laplacian? The bottom eigenvector of the Laplacian is just this blue line, the constant function. The green one is the first excited state above that, the first eigenvector above that. And if you keep on going, you get more and more oscillations. Faster and faster oscillations correspond to higher and higher eigenvalues of the Laplacian. And so for the random walks, these higher eigenvalues, the higher you go, the faster you decay. So this orange type of oscillation decays faster than the green kind, because a random walk will more quickly erase that information. The quantum version is that they pick up phases at different rates. So let's try and quantify this. Let's say the eigenvalues are lambda 0 for the lowest one, which is 0. Lambda 1, which we'll also call G, is the first one, and then lambda 2 and so on. We call it G because it's also the gap between the bottom one and the first excited state. And this represents, for the walk case, the slowest decaying mode. So the slowest decaying mode other than this blue one. And so if you want a classical walk to mix, the amount of time you have to wait goes like 1 over G. Because the decay rate is of each of these things is given by the eigenvalues. And so the lowest eigenvalue is the slowest decay. That's how long you have to wait for mixing. The quantum version is that same thing, except instead of decay, it's phase. So now, if you want to do a reflection, the amount of time you need to wait for a reflection, in other words, for this thing to pick up 0 phase and for everything else to pick up a phase of pi, that amount of time you need is going to be like 1 over G. Now you might worry with phases, it's going to wrap around, right? I'm going to get too much of a phase. So you have to do something a little bit more clever. The original way that people did this was with phase estimation. And that lets you, figure out how much the phase is without and handle the wrapping around. Now there's a more sophisticated and efficient technique called the singular value transform that does something. Basically, whenever you would have used phase estimation and done a calculation based on the phase, the singular value transform is a more efficient way of doing it, but gives you kind of gets you the same place in the end. And it turns out there are other tricks you can do, which are not the subject of. Get it, slides faster. are not the subject of this talk, which can reflect in time 1 over square root of g instead of 1 over g. And this gives a number of quadratic speedups. So yeah, should I unplug it and plug it in again? Well, my screen turned off. Yeah, but yeah, the thing is, yeah, yeah. Well, let me go back to display and so on. So, well, anyway, yeah, my computer does not see anything. Like, yeah. Okay. Well, while we're waiting for that, that can give you some quadratic speedups, and I have work with my grad student anyway on this. But that's quadratic is not going to by itself be enough to justify building a quantum computer. What can we do that will give a bigger speedup? And there's some cases known where quantum walks can be dramatically faster than classical walks. And the earliest example, which got a lot of people excited about quantum walks from really a long time ago, like 99 maybe, was the hypercube. So, again, this example of a graph, 2 to the n vertices. Let's say the goal is to start in one corner and to reach the other corner. If you do it with a classical random walk, the classical walk will quickly become uniform over the hypercube. But once you're sampling uniformly, it takes you 2 to the n samples before you will see this upper, this corner. So mixing is kind of not enough for finding this other corner. So that's called the hitting time. It's how long you start in this corner until you reach a particular target, such as the other corner. And quantum walks, on the other hand, will get there very quickly. And the time will only be polynomial in n for a 2 to the n dimension, a graph of 2 to the n vertices. And why is that? The reason is that this graph has a lot of symmetry to it. So you can group it according to Hamming weight. Hamming weight is the number of ones. So these are the vertices of Hamming weight 1, these are Hamming weight 2, and so on. And if the quantum walk starts with Hamming weight 0 and evolves, it will send some amplitude into the uniform superposition of all of these 3 strings. And then if it evolves from here, some of that will get mapped back to 0, 0, 0. Some will get mapped to the uniform superposition of these 3 strings. And so there's effectively, even though the total Hilbert space dimension is 8, there's a smaller subspace of dimension 4 corresponding to the superpositions of fixed Hamming weights. So Hamming weight 0, 1, 2, 3. And so this graph is equivalent to this one-dimensional graph where I've labeled each, I'm going to call them super vertex, according to how many ordinary vertices they contain. This one contains 1 vertex, this one contains 3, 3, and so on. And I've labeled the edges by how many edges they correspond to in the original graph. Okay? So what this really looks like to the quantum walk is it looks like it's walking on a line, maybe with some kind of hopping terms that are different from point to point, but it effectively lives in a much smaller dimensional space. Question? So this was an exponential speedup of a quantum walk over a classical walk, but there's not really a, you can't say there's a computational problem here. Like if you say the input's all zeros and I want to output the all ones, okay, well a classical algorithm could just output all ones. So how do you make this a hard computational problem that could demonstrate a separation? One way to do it would be to say that suppose the algorithm doesn't know the full geometry of the graph, but is forced to explore it locally. And this is realistic for in a number of cases. Like suppose the vertices correspond to local minima in some high-dimensional optimization problem. So often we're doing some complicated optimization. There are an exponential number of local minima. If you are at one local minimum and you go in a random direction and then do gradient descent, you'll reach another local minimum. This could form some kind of graph that you explore. And generally, if the problem is too hard to solve in closed form, we also don't have a good map of the local minimum. So you just kind of explore it locally. And there are many other examples where, like combinatorial optimization, where even if there is some structure, we don't know how to take advantage of it. So really, you should just think of it as something to explore locally. If you want to formalize that, you could say, suppose that there is an oracle or a subroutine that is given one vertex identifier, which we assume is now actually just a random string, like 000 gets back to some random string that we don't have to interpret. The only way we have to interpret it is this oracle, if you give it a vertex identifier, will spit out the vertex identifiers of all of its neighbors. So in this way, it enables us to explore the graph, but without leaking the global structure of the graph, beyond what we could figure out by local exploration. This is a model by which you can say, look, I just want to see what can we do just by exploring the graph. And it turns out there are classical algorithms that can take it with such an oracle that can figure out how to get from one corner to the other. And the reason is, if someone tries to disguise the hypercube in this way, you can still reconstruct the hypercube structure. You can figure out the bit structure of the hypercube. And the reason is, the hypercube has a lot of short cycles, a lot of cycles of length 4. If I flip bit I and then bit j, then I flip bit I again, and then I flip bit j, then I've come back to where I started, and it's a little cycle of length 4. And by exploring all these cycles of length 4, I can figure out bit structure in a way that can be consistent across the graph. And so I can use this to just, map out my local neighborhood and then just, step to the opposite corner. So this does not provide a quantum speedup of a quantum walk against any classical algorithm, just against a particular one of a random walk. So how can is there an example where a quantum walk can beat any classical algorithm? This was achieved over 20 years ago by Childs, Cleve, Yodo, Farhi, Gutman, and Spielman, with a different graph called the welded trees. Here's an illustration from their paper. The welded trees are basically two binary trees of depth n, and then with a random weld in the middle, meaning a cycle that links the two trees together. So it jumps from one side to a random vertex over here, back to a random vertex over here, back to a random vertex over there, and so on until you've connected all the vertices. So every vertex in this graph, except for the entrance and exit, have degree 3. And what happens to a classical algorithm that's exploring the graph is wherever it goes, it always sees vertices of degree 3, and it always sees new vertices, unless it's literally backtracking. But every time it explores a fresh vertex, it just, as far as it can tell, is seeing part of an infinite binary tree. Because if it was an infinite binary tree, it would just be degree 3 forever, no cycles. And whatever the classical algorithm explores is going to look like a subgraph of that infinite binary tree, until it spends exponential time. If you take exponential time, you can explore the whole graph. But short of that, you don't see any structure at all. So it evades this problem of the hypercube, and the quantum walk at the same time, again, lives in this lower dimensional space. Let's see how this looks. Here we have what we call the column subspace. Instead of fixed Hamming weight, you have a superposition across all the vertices in some column. So the entrance, that's just one vertex, and then the first layer, there's 2, and then 4, and so on. And then here I'm labeling how many edges there are from one column to the next one. And it's all kind of similar. In the middle, it's a little bit, things are a little different in the middle. I represent that by a dashed line, so the numbers are different. But it still preserves this column subspace property. A uniform superposition here will map to a superposition of a uniform superposition here, and then across the web. So the quantum algorithm just lives in a lower dimensional, a 2n dimensional space, which is much, much less than the exponential number of dimensions of the classical algorithm. Now, how can we analyze this? So this corresponds to a particle on the line. I realize this might be hard to see in the back row, right? Yeah. Anyway, it's a particle on the line, hopping is root 2. That kind of doesn't matter what the number is. What matters is that it's the same everywhere, except in the middle it's a little bit different. So I I'm teaching intro quantum mechanics now, and when do you ever need to analyze in real life particle on the line with a defect in the middle? Well, today you do, right? Particle on the line, and you want to get from one end to the other. There's a defect in the middle, so there's some transmission and reflection coefficients, which we solved at one point. And whatever the numbers are, what's important is that at least some of the amplitude gets through to the other end. And this is, what I call the platypus of the zoo of quantum algorithms. It's just so unlike anything else. There's no group symmetry here, right? There's no hidden subgroup problem. It does not look like quantum simulation of some molecule, right? Like, what is this, what is this thing like? And in trying to generalize it, I would say that there's some features of this that turned out in hindsight to be a little misleading. So, at least in my opinion. So why is that? Well, this particle on the line, here the hopping is a little bit lower, but that's kind of like having lower energy. So just to have a mental model, think of a particle on a line with a little localized attractive potential. So, as we know from first semester quantum mechanics, or maybe we've forgotten, or if you're a computer science person, you just skip it and went straight to qubits. Such potentials have one bound state, which will be localized around this attractive potential, and the whole rest of the spectrum will be delocalized. So almost all of the spectrum is going to be spread out over the entire line, except for that bound state. And so from the quantum algorithm point of view, what that means is it's very easy to get from one end to the other. There's pretty much only one eigenstate that can screw things up, and that is the ground state. So adiabatic evolution fails. Adiabatic evolution means you start in the ground state in Hamiltonian, you change the Hamiltonian slowly enough that you always remain in the ground state. And so if you try to have your Hamiltonian be the adjacency matrix, and the ground state is this one localized state, then you get stuck. And that confused people for a while, until Nagai, Soma, and Kivarova figured out if you do the adiabatic algorithm a little too fast, then you'll bump up to the first excited state, and that, like everything else, is delocalized, and so that first excited state will get you to the end. I mean, I guess you also need that to be separated from the rest of the spectrum, but that's not too hard to show. So it's misleading in the sense that the quantum works extremely well. You can do almost anything other than be in the ground state, and you'll get to the end. At the same time, it's also a little misleading in that the classical lower bound uses arguments that that basically make the graph very rigid. So I would say that people who did this were a little traumatized by all those cycles in the hypercube. They said, I don't want any short cycles. Short cycles leak information. So, what's a good graph that has no cycles? The tree, right? That's what it means to have no cycles, is to be a tree. So let's just be tree-like until we get to have 2 to the n vertices. And it's so big that no one can see any structure. And so if you try and modify this and put in a few cycles, their proof breaks right away. And then if you don't have cycles, then you have trees and you basically have this graph. In fact, the first thing they tried was to take 2 trees without a random weld, and then you can figure out what's going on. So it's the classical lower bound avoids cycles and then makes this quite rigid. And then the quantum one, also, these properties that are so generous also are somewhat unique to this graph. So what we wanted to study was how can we generalize? How can we go to a larger family of graphs and get a broader family of quantum speed of trends? And what we're considering, the feature that we're keeping from the welded tree is we're keeping this hierarchical structure. So we're assuming that you have some graph, it's fairly general, but the vertices come in groups, which you might call super vertices. Any questions, by the way? I feel like I've talked without pausing. Any questions about earlier stuff?
When you map from the classical graph where you partition vertices into the weighted edges,
Yeah.
they seem to have different weights as you move along, but then somehow the quantum equivalent seems to have like equally weighted edges.
Oh, good. So this number is the number of edges, and this is the hopping strength. And I'll get to that in 1 minute. I'll show you how to calculate the hopping strength. Yeah, good question. So it's an interesting relation between the classical, the edge structure of the graph and the effective hopping strength. I'll show you the one second. So in this hierarchical graph, you have these super vertices that are like groups. So this one has 2, so I write a 2 over there. This one has 8, I write 8 over there. They don't have to be powers of 2, but it makes it a lot easier to draw. Because I want the one regularity condition I want on this graph, what does it even mean that it's hierarchical? Is if you take 2 super vertices and you look at a vertex, one vertex from here, ask how many edges does it have to this entire super vertex? I want that number to be the same for all vertices within this super vertex. Okay? So this one has 2 edges to this set. That means this one also better have 2 edges to this set. I guess here it's 1. This one should also have 1 edge to this set. This one should also have 1 edge to that set. Okay? So that is the regularity I want. Samaretti's regularity 11, it's kind of in that spirit. Basically, I can group it into, people also do this in, this sort of thing is also done in social networks. If you try to model a social network mathematically, you might say, well, there's groups of people, like there's adults and kids and whatever, and each person has the same number of edges to all of all of the other groups. Like each, I'm saying this very well. The number of edges that an individual has to another group only depends on that individual's group identity. So how do you get the hopping terms here? Actually, I guess that's on the next slide. So you get these effective hoppings that look like this. Some square root of 2s, some 1s. It turns out the square root of 2 if the size is changing. Actually, that should be a square root of 2. And 1 if the size is the same. And the formula for it, I'm going to illustrate this in more detail in 1 dimension. Yeah, question?
Sorry, can there be edges between vertices in the same super vertex?
There can be. Yeah, great question. Didn't hear that was, what about edges within a super vertex? And I'll come back to that. I want to avoid that. Basically, for now, let's just say no. And then later I'll talk about why. Yeah, good question. Yeah?
Well, also, like, if someone just gave you that graph without drawing the circles around it, if they were just sort of randomly placed, is it easy to like assemble it into the super vertices? Is that like a relatively straightforward operation, or do you have to like know in advance? That structure.
Yeah, it's a good question. Should be. So I guess the one thing I'll say is that the algorithms do not know about the circles. Okay, so they're just given the graph, and the circles are just present for the analysis. I think it wouldn't be too hard to find the circles if you're willing to do runtime proportional to the size of the graph. One thing that gives me a little pause is that they could be ambiguous, like there might be more than one way of partitioning it that's valid. So, I mean, the way I think about this, which kind of gets at it, is you can think of this like a Krylov subspace. For those who don't know, these are things that come up in numerical linear algebra. So you have a vector. Look at a vector V and a matrix A, then you can just consider V and then AB and then A squared V and A cubed V, and like all of the vectors you get by acting on V over and over again with A. And these form a linear subspace. And what's going on here is that you start with the initial vertex, and then you take the Krylov subspace formed by hitting with Hamiltonian over and over again. That's going to be a low dimensional space. And so kind of what you want to do is you want to find that Krylov subspace. And that's certainly something you can do to, I kind of described the algorithm for doing that. And then how you slice it up into groups, maybe that's, you have multiple choices there, but the important thing was the low dimensional subspace. Okay, so let me illustrate this in a little more detail with a one-dimensional supergraph. You can do it for any, for any graph, but 1D we can analyze it in detail. And to get a sense of how this is like the welded tree, right? The welded tree also reduces the line, but now I don't need it to be a tree. I just need regular connections from one layer to the next. There's these short cycles. And the sizes don't have to just increase. They can increase, decrease, increase again. They can do whatever. I do want the sizes to change slowly. I want each thing to move in a constant or maybe polynomial multiple of each other. I don't want to go up in size exponentially in one jump. We could probably handle that, but it would be inconvenient, and I think that's anyway less natural. So if you have such a graph, how is the quantum walk going to behave? And to do this, we want to find the effective Hamiltonian, which there was a question about a minute ago. How do you find the effective Hamiltonian from a graph? And what you do is you first do the counting, like how many vertices are in each super vertex, call it S0, S1, S2, and so on. Then how many edges are there from one super vertex to the next? Let's call it E01, E12, and so on. And then you just, you want matrix elements. On one side is the superposition of all S0 vertices here. On the other side is the superposition of all S1 things there. And so you can see the hopping amplitude is just going to be the number of edges divided by the geometric mean of those two sides. So just write it out, that it kind of falls right out. And so now we have a particle on a line hopping with a variable hopping strength. Yeah.
Thanks. I just have a clarifying question. Is the original Hamiltonian describing how you would navigate the graph or how you build the graph? Or is that kind of the same thing?
Oh, yeah, I didn't say that part. The original Hamiltonian, I was thinking of it as either the Laplacian or the adjacency matrix. They're kind of the same up to a sign. So it's just you put a 1 wherever there's an edge. And when doing quantum walks, just like classical walks, you could put different numbers on different edges. You can make them chiral and put phases and so on. And there may be advantages to doing that. For now, I'll just stick with the simple case. But yeah, so I'm just going to put, for every edge, I'm just going to put a 1, like in the adjacency. Good. So, okay, so how can we analyze this Hamiltonian? Yeah?
Does it matter that you move with regularity in this graph here? Like in previous times, you were mentioning like all of your edges were the same number of degrees, whereas like it seems like for some of them here, like you got the vertices with degree 2 and degree 3.
Yeah, I guess I do want it to be regular actually. So I probably should have drawn that differently. The reason I want it to be regular is that way, if it's regular, then the classical algorithm will get lost. So that part would be important to the classical algorithm not being able to know where it is in the graph. So yeah, so I should have. Yeah, sorry about that. I should have drawn that differently. Yeah, it's kind of a lot of edges to draw in PowerPoint. I should have made it more realistic. Or done programmatically. Yeah.
Okay, so for the simple case where you have like a binary graph, I guess connected just directly to another, or binary tree connected directly to another binary tree, does that correspond to the effective like picture you get to like kind of like a sticky state where your coupling is essentially equivalent to that case? Or like super radiance? Like, is it the same type of math in that simple case?
So by this you mean like if you have this type of graph.
Yeah, but maybe without the welding step in the middle being so random, but yeah.
So it actually doesn't matter if the welding step is random or not.
Okay.
The randomness is helpful for confusing the classical algorithm. From the quantum point of view, you just care about how the uniform superposition here comes to the uniform superposition there. So for that, only regularity matters.
Okay.
And then, yeah, I don't know actually what the connection to super radiance would be, but probably because of my ignorance of super radiance.
Okay.
But maybe afterwards we can talk about that. We can
Sure. Yeah.
I'd love to hear about that. So, Okay, so let's analyze this Hamiltonian. So what have we done? We started with a graph that was hierarchical. We restricted the Krylov subspace. We have this effective 1D Hamiltonian with variable hopping rate. Now we want to analyze it. In the welded tree, the hoppings are almost all the same, but we want to be more general. So you can imagine all kinds of different ways of getting hoppings. One simple class that we analyze, and I think a good way to test how generic speedups are is to pick them to be random. And so, if you want to test kind of how much can these 1D supergraphs get speedups, the welded tree is a very special case. If you want to do something broader, choose each of these t's to be random. Actually, more precisely, what we'll do is we'll choose their ratios to be random, but independent and random. Then we'll see what we get. So the effective Hamiltonian has zeros on the diagonal and has these t's on the off diagonal. And for convenience, it'll be convenient to choose the number of vertices here to be odd. And you can do it with it even, just if you do something slightly different. So I'll just illustrate the odd case. The reason why that's significant is for matrices of this form, the eigenvalues come in pairs. Every time an energy E shows up, minus E also shows up. So that means if the number of vertices is odd, there's going to be a zero mode, or maybe an odd number of zero modes, so at least one. And right in the middle of the spectrum, and then the rest of the spectrum will be a positive part and a negative part that are mirror images of each other. And we're going to be interested in, we're going to use a zero mode. We're not going to use any other part of the spectrum. And we're going to be interested in two properties of it. First, it should be delocalized, meaning that both the entrance, this zero state, that means superposition over the entrance nodes, and the six, the exit, both of those should have non-negligible overlap with the zero mode. And then the other property is that there should be a decent gap to the rest of the spectrum. Okay? So those two properties are non-obvious. It's also maybe not obvious why they're useful. But I'll explain both of those on the next slide. Okay, so that's going to be kind of the high-level picture. We choose this Hamiltonian in different ways, let's say a random, and then we know there's a zero mode, and then it turns out it has those two properties. The quantum walk will be successful in getting from the entrance 0 to the exit 6. Okay, so how do we analyze that? Let's write out the amplitudes of the zero mode. So psi is going to be the zero mode, meaning it has energy 0. Here is amplitude, psi 0 through psi 2n. Turns out that the solution you get is only supported on every other vertex. That's where all the amplitudes are. And then this equation, h at psi equals 0, is super simple in terms of the amplitudes, because it's on a line. You just have these linear equations that just have two terms in each one. So what that means is if you know one amplitude, let's say psi naught, then you can just read off all of the others from these equations. Psi 2 is just going to be psi naught times some ratio of T0 and T1. Then psi 4 will be related to psi 2 in the same way. And so you get that the 2K amplitude is just psi 0 times this product of all of the ratios of hopping terms. Okay? So you have these random T's, and then you just, to get any amplitude, you just multiply together a bunch of their ratios. Okay? And now how can we understand what that's going to do? In the simplest case, take the T's to be random. And so you start off with some psi naught, and then to get to psi 2, you multiply by a random number. Psi 4, you multiply by another random number from the same distribution, and so on. It's a multiplicative random walk. And we know for an additive random walk, if you take n steps, you get a Gaussian with standard deviation root n. And so the multiplicative version, you just get e to a Gaussian with standard deviation root n. So you get e to the plus or minus, e to the something random that's like plus or minus root n. And so what that means is that the amplitudes, the ratio of the biggest one to the smallest one is going to be like e to the root n. And in particular, that means that the beginning and the end, the 0 and the 2n states, their participation in the 0 mode will be at least e to the minus root n. You know, it could have been worse. It could have been exponential. It could have been like 2 to the minus n, right? This is instead 2 to the minus root n. So it's a lot more than it could have been. And a similar argument suggests that the gap, or can prove actually that the gap is also 2 to the minus root n. One way to get intuition for this is these amplitudes are going up and down, but the lowest amplitude will be like e to the minus root n. And if you want to get a state that has very low energy and is orthogonal to this one, what you can do is you can take this state and flip the signs of half of it, or of some good fraction of it. So you're going along, the amplitudes are going up and down and up and down. And when you get to a point with this really little amplitude, then flip the signs and everything from there on. So this will look, if you're just comparing neighbor to neighbor, this will look the same as the original state, have the same energy as the original state, except at this point where you flip the signs. And there, the amplitude was 2 to the minus root n. So the energy that you'll add by doing this is 2 to the minus root n. And yet, by flipping the signs of a good fraction of it, you've got something where if it's not orthogonal, the inner product is substantially less than 1. So it has a big orthogonal component. So this is kind of a hand-wavy reason why you might expect in such a situation the gap would also go like 2 to the minus 1. Okay? So in the condensed matter literature, this would be called being localized, because you have exponential decay with root n. However, we'll see this is still useful from a quantum algorithm's point of view. Okay, so that's just the spectrum. That's the state. What is the algorithm? Let me say that in a second. This is also probably the most technical part. So pause any questions? Yeah.
I thought you said on the previous slide you wanted a big gap, but it sounds like the gap you were describing here would be very small.
Yeah, so it's 2 to the minus root n. So is that big or small? Let's come back to that. So let's talk about the algorithm, and then we'll come back to this question. Is that, how do we feel about 2 to the root n? The algorithm starts in the entrance, which is het 0. And then imagine that what I do next is I measure the energy eigenbasis. Okay? If I could perfectly measure the energy eigenbasis, and I know that the 0 mode has some non-negligible overlap with the initial state, well, then there's a chance that I'm going to end up with 0 energy. In other words, with the 0 mode side. Okay? So the first step is I start in the entrance. Then I measure the energy eigenbasis. Then I measure again in the condition basis. Now, the exit node also has non-negligible overlap with the 0 mode. So I have a good chance of landing in the exit mode. So that procedure has a good chance of getting me from the entrance to the exit. And by good, I mean 2 to the minus root n. So if I repeat this thing 2 to the root n times, then I will succeed. Okay? Now, let's go back to this part about measuring the energy eigenbasis. Realistically, you can only do that with some finite resolution, right? If you run for time t, then your resolution is going to be 1 over t. And how much resolution do you need? Well, how far, let's go back to this picture, what's the gap between the 0 mode and the rest of the spectrum? If that gap is g, then the amount of time you need is going to be 1 over g. And I argued that the gap will be like, again, e to the minus root n. And so the amount of time you need is going to be e to the root n. So we kind of keep multiplying these e to the order root n's, and we get in the end, the total time is e to the order root n. Okay? And you can do this, instead of measuring, you just need to dephase in the energy eigenbasis. You don't need to know the answer. And so what you can do is you can do Hamiltonian evolution for a random amount of time, where it's a random number chosen between 0 and 1 over the gap. And it turns out that will effectively dephase in the energy eigenbasis up to an energy resolution of g, which is enough for our purposes. Okay, so yeah, is 2 to the root n big or small? And more generally, let's compare this with classical. So let's suppose the supervertex sizes are S0, S1. The ratios between them I want to be order 1, which means the hopping amplitudes will also be order 1. I just argue the quantum runtime will be exponential in root n if the ratios are random. The classical runtime, the classical algorithm is going to get lost in the largest supervertex. Whatever the largest supervertex is, that's sort of a proxy for how big is the overall graph and how many vertices will the classical algorithm have to explore before reaching the exit. And the biggest supervertex, you can that size comes from just the product of all of the ratios along the way. And you can think of that, and that in general is going to be exponential in n, because you're multiplying together and you increase over if little n is the number of supervertices, and each supervertex is twice the size of the last one, then you're growing exponentially. So you're comparing 2 to the n versus 2 to the root n. And that's called a super polynomial speedup because it's more than any polynomial speed, right? Polynomial would be 2 to the n goes down to 2 to the n over 2 or 2 to the n over 5 or something. So 2 to the root n is better than any polynomial speedup. It's not as good as maybe an exponential speedup, bringing it all the way down to polynomial n, but it's way better than anything like root. So it's a very big speedup, while still not as big as the exponential one that we expect from something like short term. The other interesting thing about this is that the quantum runtime depends on the variance of the log of these ratios. Because remember, you're doing this random walk, and you kind of want to know what's the top of the walk versus the bottom of the walk. That's like how much are the fluctuations. And the classical one depends on the expectation of the log of this ratio. You just kind of want to know how big do the supervertices get when you just keep on multiplying these ratios. And so you could tune those things separately. And that's in a sense what the welded trees did. Is they said the ratios are all equal to 2. So the variance is 0, making the quantum one very fast, polynomial time. And then the classical one is still exponential. And so that was kind of finely tuned. And so it's interesting, what happens when you break it? Does everything fall apart? Well, it's not polynomial versus exponential, it's 2 to the root n versus 2 to the n. Still a substantial speed up, even if it's not, that's what you get you get to be more general, but the speed up is not as dramatic. Yeah.
So if you make the Ri all almost equal, do things start looking more and more like the welded trees graph? Does that mean?
Yes.
Okay.
That's right. So you can do more general graphs. I want to get to other topics. I want to go into this in great detail. We have to impose an additional condition on the hopping terms. For it to work, they have to satisfy this gauge condition, so the graphs become, in some ways, less natural. The one thing I'll just briefly say is that the quantum walk works a lot better in this case. Roughly speaking, in 1D, it's easier to localize. In higher dimensions, delocalization happens more readily. And so if your supergraph is a 2D lattice, then your quantum runtime is what's called quasi-polynomial. Exponential in poly log n. So exponential in log n would be polynomial, right? This is exponential in poly log n. And then if you're in 3 or more dimensions, the quantum runtime is just polynomial. So it gets better as the connectivity increases, but you do have these kind of annoying gauge conditions. One thing we're looking into doing, the paper's already getting long, is to relax the gauge condition. Do you still get something, like maybe you get a 2 root n? I don't know, we're trying to figure that out. That's not good. So just to summarize, the classical algorithms have to explore most of the graph. The quantum algorithm speed depends on the localization transition. If you're delocalized, you're very fast. If you're localized, you still get a speed up, it's just not as dramatic. Now, for the very patient experimentalists in this talk, who suffered from me talking about exponentially large graphs specified by oracles on quantum computers that are some distance away, let me talk about something that might be implementable sooner. And here is work that is really very partial and incomplete, but hopefully thought-provoking. Can you implement, what kind of interesting walks can you implement on existing platforms? And what I've described is, I want to speed up, and I'm going to take this very narrowly defined welded tree and generalize it a bit, and hopefully we'll start moving towards realistic. now I'm gonna start with realistic and move towards big speedups. And so you'll see the speedup will be less convincing, but the implementability will be more convincing. So something that Misha Lukin's group has started has been using Rydberg atoms for the maximum independent set count. So how does that work? You have these atoms, you can put them in a 2D array of your choice, and they obey this Hamiltonian, where if two atoms are adjacent, there's a term that gives an energy penalty for them both being in the excited state, in the one state, and otherwise there's no interaction. And then there's also a sigma x term on each qubit. And they work in the regime where B is very large. Think of it as basically infinity. So what that means is that two qubits cannot, if they're next to each other, they cannot both be one. They can be 0, 0, 0, 1, or 1, 0, and the rest is just forbidden. And so let's illustrate with an example. Suppose your atoms are just in this little square. Then I'm going to draw the configurations as white or empty for 0 and red for 1. So here is all zeros. Oh, I'm sorry, I should say, what does it mean when you have a graph and you're putting zeros and ones on the graph with node 1s connected by an edge? The set of 1s is basically a set with no edges between them. That's called an independent set. Okay, so the allowed configurations of where the 1s are, those are the independent sets of the graph. And so for the square, what are the independent sets? Well, obviously the empty set is always allowed. Any single vertex, always allowed. Pairs of vertices are allowed if they're not touching each other. So they have to be opposite corners. And then the green lines are the edges that you get by single bit flips caused by the X interactions. And so what happens, we have this effective state space that is defined, it ticks a lot of our boxes. It's exponentially large given the input, right? If you have n vertices here, there'll be an exponential number of independent sets. But it is, this combinatorial space that we're moving between with local moves. We can implement the quantum walk on this space. And now we'd like to know the properties. We want to start here and maybe get to the biggest independent set, some other point in the graph that we'd like to hit. Okay, so this is something we'd like to analyze. And just, before I get any further, I would like to use the tools of the earlier part of the graph to say dramatic things about this. I do not know how. So all I can say is this is a compelling platform to look for quantum walk speedups. And let me tell you the speedup I do know, which is not an example of the ones I did earlier, but I think it's still intriguing. So, given such a graph, what are cases where quantum walks can beat classical algorithms? Or at least can beat classical random walks. That's how we started with the hypercube. Let's just start with something tangible like that. So here is an example of a graph that is really hard to optimize independent sets on with local moves. And the graph is basically a star with one vertex in the middle, which I've colored yellow. I'll tell you more about that later. And with n arms coming up. And each arm has length 2. Okay? So what are the independent sets? Well, you have a couple of choices. If you pick up the vertex in the middle, that's the independent set. Then the inner ring is all forbidden, and then you can choose all the vertices on the end, and you can get an independent set of size n plus 1. That's one choice. The other thing you could do is not include the yellow vertex. Now every arm presents you with an independent choice. Pick one vertex or the other. Or neither, I guess. But if you do one vertex or the other, then you get an independent set of size n. And there are 2 to the n such choices. So what that means, actually I think there's even a little bit more than this. There's actually slightly more than 2 to the n independent set with size n, and there's a single independent set with size n plus 1. So there are a ton of local maxima that are right below the global maximum, and most of them do not connect to the optimal. So simulated annealing will get stuck here. you try to explore randomly, you will not find the maximum. Turns out the adiabatic algorithm also fails here. But this is an old paper by Farhi, Goldstone, and Gutman comparing adiabatic to simulated annealing. They phrased it a little differently. If you look at that paper, this is called the bush of implications. I'm not going to explain the connection, but pretty direct connection. It turns out they argued, well, let's change the x field on each vertex, have it be proportional to the number of connections that it gets. And if you do that, now the adiabatic algorithm will find this optimal solution. And for similar reasons, quantum walks will also find the optimal solution. Simulated annealing, if you turn up the hopping rate of the middle vertex by a factor of n, that will still not help simulated annealing. So whether this is fair or not, to sort of treat the middle vertex separately, you could debate that. And anyway, this doesn't matter. It's not a very it's not a very generalized general family. But if you do that, adiabatic and quantum walks succeed. This is something you can do at least with two species Rydberg atoms, if you put a different x field here. If you want to really make it look like a graph, you say, I don't want to have a yellow colored vertex, that just looks like cheating. One way you can have a graph is to pile n vertices in the middle, really close together. Then these things will all move correctly. Actually, this kind of looks like super radius here, because these sort of Rydberg blockade each other, only one of them can be excited, but you get a superposition of the excitation being in all n of these. And so that effectively enhances the x coupling, the x field on these in a way that is equivalent to, instead of manually scaling a depth field, you just put more vertices here, and that will do the same job. And this one, unfortunately, does not fit into 2 dimensions. The way I drew it, it does, but the scaling goes with n, right? So as you crank up n, I try to have reasonable demands of experimentalists, but this would require increasing the number of spatial dimensions, to n over 2. So that's maybe not a reasonable demand. But what you can do is you can realize it even in 2 dimensions or even 1 dimension if you use separate species for each layer. And people have recently started doing this with Rydberg atoms. So this is, getting towards something practical, at the cost of giving up a big provable speed. Okay, so about out of time, let me just briefly address some things we're continuing to think about. So there's a question about what about edges within a supervertex? Well, if those are all the same, that adds an identity term. If they vary from supervertex to supervertex, this is now diagonal disorder. We'd mostly been considering hopping disorder. Diagonal disorder localizes you a bit better. And so that is less favorable to the quantum algorithm. And of course, the other way you can deviate from our picture is you can break the regularity a little bit. And so if you try to apply this to a real optimization landscape, kind of another challenge is that these are hard to analyze, you start violating these nice assumptions I've made that have been nice to the algorithm, but make it apply less well to problems. And it's an ongoing question of how well can these walks survive these types of deviations from the ideal I've described. Another thing we're thinking about is how can you realize the oracle within a computable function? And there are ways of doing this from simulated annealing, which we'll get into, but I'll say that's a route towards an explicit function. And a further application is there's work by Hastings and Gillian and Vazirani on oracle problems that adiabatic evolution can solve exponentially faster than any classical algorithm. Those use some quite contrived graphs, and with our techniques, I hope you could get this work with a more general family of graphs as well. That's another, adiabatic is related to quantum walks, and that's something that we're continuing to look at. Okay, so I think I'll stop here. Thanks everyone for your attention.
As usual, we'll let students ask questions first. There are remaining student questions.
Maybe was wanting to clarify, like, is the reason that the Rydberg atoms are harder to deal with, in a analytic form than the previous part of the talk, like the type of interaction versus like Ising versus spin exchange, or is it something else that is at
No,
play
it's
here?
just very, and this is just a very common feature of algorithms work, which is if the problem comes from the real world, like distinguishing images of dogs and cats, then it's very messy. And if the problem is something mathematical that you've written down with the goal of making your algorithm work, like the hidden subgroup problem or the cyclic group, then it's very clean and easy to analyze. And so it's just a matter of the Rydberg implementation was there, that's what you can implement in the lab. And then we just have to work with it. And it doesn't fit our algorithmic structure. Too bad for us, we don't get to keep changing it until it fits our structure. And that's sort of the high level reason. If you want a little more specific one, I chose the graphs to, the hierarchical graphs have nice properties. This defines a graph that's, this independent set graph is something which one can define, and we just don't know its properties, right? And I guess I would say one more thing about, in general, it's a little bit vague, but I think it's a nice, it's kind of my favorite reason why I think NP complete is worth looking at. Like, if you think about what separates an NP complete problem from a problem you can do in polynomial time, the NP complete problem often lacks the kind of mathematical structure that is amenable to algorithms. Like, you can compute the determinant in polynomial time, but not the permanent. And the determinant corresponds to the eigenvalues, where there's all kinds of, you also have decompositions in terms of the eigenvalues and all kinds of structure around that. And there's sort of no analogous structure for the permanent. And so, and the NP completeness is almost like a proof that there's no efficiently accessible structure that would be useful for the permanent. And so the fact that independent sets are NP complete to optimize is very strong evidence that the graphs associated with them do not have the nice structure that will lead themselves to nice math. This is not a proof, and there's always a possibility for creativity and luck, but that's just sort of my intuition for why, when you're talking about solution landscapes for NP hard problems, the fact that the problem is NP hard also suggests that the landscape will be hard to analyze. Although, maybe there's still heuristics and so
on. When you were discussing the sort of features you want your graph to have, things like this gauge theory for the or gauge condition for the more general cases, are these conditions things that naturally emerge from the graph for whatever system you're analyzing, or can you actually engineer them into your graph?
I don't know. That's a good question. Yeah. And I guess the reason I don't know is I haven't told you how these graphs come about from natural systems that we're analyzing, because we haven't found ways of doing that yet. So what I should have, drawn a picture of a bridge being built, where like one little end's been built and the other little end. That's kind of like the stratosphere, right? So this is one end of the bridge, right? And the other end of the bridge is these independent sets from Rydberg. And the middle of the bridge is missing. So once we have the middle of the bridge, we'll know how natural those gauge conditions are, right? And you know what I mean? So that's the status that we researched to date. And while that's not so great, the good thing about it is that it's a new corner of quantum algorithm space, which was previously underexplored. But maybe this sort of gives you a sense of just how little of the forest we've mapped out.
Yeah, I want to understand a bit better the connection to physical implementation. So in the Rydberg case, you considered essentially each step of the walk is kind of this, it's essentially adding an excitation.
Or taking it away.
Or taking it away, but it's X.
Yeah.
You could also imagine having some graph and having like a spin exchange interaction on the edges, which would really be like sort of a particle that's popping on the graph, right? Would that be different?
yeah, so I thought about that a little bit, and I can't remember the conclusion. I guess there's kind of two versions of that, right? So you could add another term to the Hamiltonian, which is like the sum of BI, right? Which will force you to stay within the same layer.
I was just imagining like I start with an excitation on a particular site and then fill out the file. So basically,
I understand, yeah. I guess maybe what I would say is take those x terms, and then there's, in a sense, what you're talking about is just applying like h squared, like just applying it twice. You apply the x terms and then you apply it again, right?
I'm not sure. I was imagining like a sigma plus I, sigma minus j.
Right. So this thing can move from one site to the other one.
Yeah.
Okay. So yeah. So maybe the difference between what I said about squaring the x terms and what you said with the sigma minus and the sigma plus is whether you're restricted to the same level or not, right? Because that one would conserve the total number of excitations, and then the squared version, there'd be some possibility that you kind of move two away, and I think it's,
Sorry, it would be a different mapping, right? I was more just wondering like in the particle hopping.
yeah.
On the lattice, like a more directly connected to the sort of one walk that you started from.
Well, oh, you mean in the first part of the talk?
Yeah.
So in the first part of the talk, so the thing that's weird about this is what exactly is each of these vertices? Physically, you might think of it like there's one particle that can be in a very large number of locations, but that's not a good route to a quantum speedup, because if there are 2 to the n locations, that's kind of like writing my data in unary, right? It's like what's the particle count? It'd be all zeros except for 1 where the particle is, and that's just not efficient. So I really need it to be in binary, which means that these are not physical locations. These just correspond to different bit strings. You know what I mean? So I cannot, like, these things could never be like a particle actually hopping around. It could only be some kind of graph of configurations. Like you hop from one configuration to another configuration. And that could emerge from the kind of dynamics you're saying. So let's say, and those dynamics, they wouldn't quite fit the goal of maximum independent set because they keep the number, they would keep Hemingway the same. But there are plenty of other combinatorial optimization problems where that would be what you'd want to do. In fact, there are combinatorial optimization problems where maybe you say, I fixed the Hemingway, and then I want to optimize something to that. Like an example is graph partition. I want to take my graph and divide it into 2 halves, that have some property, like maybe it minimizes the number of edges cut. And then I have a hard constraint, which is 2 partitions should have exactly n over 2 vertices. Then it'd be really good to have number preserving things. But now let's think about the hopping. So there's the hopping in the Hamiltonian, which is one excitation goes from one site to another one. But then it's moving, then the configurations, you're also hopping from one configuration to the next. The number of configurations is exponentially larger, n choose n over 2. And when I think about localization or delocalization, I really want to be thinking about it in this larger space, because I'm doing a quantum walk within this larger space. So it's kind of like there's this physical thing which is small, and then an exponentially larger space of configurations, and I'm walking within this configuration. And it kind of has to be that way if I want to get a speed.
How can you define a graph for quantum walk on the continuous optimization landscapes, and what can it achieve?
Yeah, that's a good question. I don't know to what extent people have done this. What I had in mind was, I know that for continuous optimization, you have an exponential number of channel points, certainly, but often an exponential number of local minima. And you can move around in the landscape by making some random moves and then following with gradient descent. And so in that way, you would go from one local minimum to another one. So this is an example of something that you could do with a, this corresponds to what people actually do in classical algorithms like simulated annealing. And so it also defines a random walk over an exponential number of vertices. So as for what you can achieve, well, that depends on the performance of algorithms on it. So we don't have results there because to do that, we'd want to characterize in some way the landscape. And here, maybe the NP complete thing was a little pessimistic. There are heuristics that describe the overall statistics of local minima in these landscapes. So there may be something you can say there. Yeah, this was more, I guess the way I think about it is to do these quantum walks, for these to be interesting, what you need to do is you need to have, kind of like I was, the answer to Monica's question, you want to have an exponentially large configuration space. You start off, you always have n bits or n qubits. And then from that, you define an exponentially large configuration space. And then, you want to either quantum walk or classical walk within the configuration space. And so how can you succinctly describe large but interesting configuration spaces? And so, the space of all local minima is one such example. Combinatorial optimization gives you other classes of examples. So I'm not saying I'm not mentioning these because we've solved them. It's just these are the types of examples that we should be looking at for quantum speeds. And I think it's it's worth bearing in mind that as if you want a quantum speed up, like these, it's almost like getting the syntax right. Like you can't do something in unary, for example. You have to be thinking in terms of these combinatorially defined spaces.
If there are no more questions, let's thank Aram again.